In this video, we're going to see half-wave rectifier, its working, and some of the parameters. As we have discussed in the previous video, that first the AC voltage that we get from the main supply should be stepped down. So we have first the step-down transformer. The step-down transformer primary winding, which is on the left side, let's say has N1 turns, and the secondary winding, which is on the right side, has N2 turns. Then the voltage relationships would be V2 over V1 should be equal to N2 over N1. And in general, the voltage at the primary winding would be the main supply, which would be 220 volts RMS at 50 Hertz. Let's say N1 to N2 ratio is 10:1, which means, let's say this is 1 over 10 as it is step down transformer. Then the voltage at the secondary winding would be equal to 1 over 10 times V1, that is, let's say 220 volts RMS, since it would be equal to 22 volts RMS at the secondary winding. So the voltage for reference, let's say the voltage that we get here is, let me call this VI. This is the input voltage to the rectifier circuit. So this voltage here would be a sinusoid voltage which has both positive and negative half cycles. Now, to increase the average component in this waveform, of course for this waveform the average component would be 0 because it's a pure alternating current or alternating voltage. So in order to remove the negative half of it so that we have non-zero average value, we need to remove the negative half of the wave. So in order to do that, we have a PN junction where when it is forward biased, it acts as a short circuit. When it is reverse biased, it acts as an open circuit. So we're going to have that device here, which is a PN junction diode, and connected to a load resistor, RL. And the voltage that we would see across the load resistor, we would call this as the output voltage. And any current that would flow through this circuit, let's call this I. Now coming to the working of it, how this circuit is going to work. So let's take it into two segments where the voltage VI is positive. That's the first case, when VI is positive. So obviously the sinusoid wave, this VI is equal to Vm sine omega t. For simplicity, let me say this is the angle and let's call this alpha. We can write this as Vm sine alpha. So let us say in the first case that we are talking about the first half cycle, which means alpha is in between 0 and pi. In that case, so let me show only the secondary winding and the circuit following it. So we have here the secondary winding where in the first half cycle that the upper side is positive and the lower side is negative, hence VI is positive. So we have the first half cycle during which the P side of the PN junction diode is at higher potential compared to the N side, which means the diode would be forward biased. When diode is forward biased, considering it as an ideal diode, we would have a short circuit. Because the diode is forward biased, it will allow current to flow through it. Then we have a load resistor, in which case the amount of current that would flow would depend on the load resistor. So we can write that I is equal to VI over RL. But in reality, the diode, when it is forward biased, it offers some forward resistance. So if you consider that, then the current would be equal to VI over RF, the forward bias resistance offered by the diode. What we have seen here is a short circuit. Instead of that, if we have a forward resistance, then the resistance seen by this current would be RF plus RL. Then we can write this again equal to Vm over RF plus RL times sine alpha. So this quantity Vm over Rf plus RL can be called as Im. So now we know what is the current in the first half cycle of operation, where the diode is short circuited and there is current flowing in the circuit. Let's come to the second case, in which Vi is negative. Vi is negative. So let me take the circuit here. In this case, as Vi is negative, the upper side would be negative potential and lower side is positive, which means the P side of the PN junction is at a lower potential than the N side. Hence, the diode would be reverse biased, in which case it would be an open circuit. In fact, there would be some leakage current flowing, but for our simplicity and understanding, we'll take the current to be 0 here because it's like an open circuit. The amount of current that's flowing is negligible. So let's say I is 0 here. So to logically represent, what we are talking about here is the voltage is in the negative half cycle. Now we can write in this case that we're talking about alpha from pi to 2 pi, in which we are in the negative half cycle, where the current is equal to 0. So now, as we know what happens in positive and negative half cycles, because of the diode, there will be conduction only in the positive half cycle, whereas in the negative half cycle, there won't be any conduction of current in the circuit. So let me represent what happens to the current in the first case here, that we have current following the voltage, whereas in the second case, of course here we have to represent what happens in the first one as well, but in the second case it would be 0. So the same current flows through even the load resistor, hence the voltage that we would see at the output side would also be of the same manner that of the current that we have seen. So let me write that current equation here. The current that we have seen is equal to Im sine alpha, when alpha is in between 0 and pi, the first half cycle, and the current would be 0 in the second half cycle, where alpha is in between pi and 2 pi. So given this, let me draw the waveforms for the Vi, the input voltage, and the currents that we have here. Let me take, this is the Vi, that is the input voltage, and this is the current. So we know that in the positive half cycle, we have the diode on, which makes the current to flow through the circuit, where we get current flowing, and in the negative half cycle, the diode is off, which makes the current 0 in the circuit. And again, in the positive half cycle, there would be current flowing because the diode is on, and it would be 0 in the negative half cycle because the diode would be off. And as we know that the voltage, output voltage, which is across the load resistor RL, would be equal to I times RL. So the nature of the output voltage would be same that of the current that we have seen here. Now, having seen the current equation and the current waveform, now we can find out some of the parameters corresponding to the current, that is the DC component or DC output current. This value can be taken to be as IDC. In fact, any periodic wave can be represented in terms of Fourier series. In Fourier series, we would have a DC component and AC component for a given waveform. But as we look at this waveform, that we have positive area within the given period. Let's say this is 0, this is pi and 2 pi. Within this region, we have positive area. When we divide that in the given region 0 to 2 pi, we would have a positive value, which is the average component is present, which is not 0. That was the intention to start having the rectifiers, to have an average component, which is DC component. So to find this value, the IDC is given by 1 over 2 pi. That is the region over which we are going to find the area. That integration 0 to 2 pi I d alpha. And we know this can be written as I is divided into 2, that is 0 to pi, where we have this is I am sine alpha d alpha, plus from pi to 2 pi, this quantity, the current is 0. So this entire term would be 0. So this integral is going to give us the area under the curve I. And when we divide that with 2 pi, we're going to get the average value here. As the second term is 0, we have only the first term. So let's find that out here. That is 1 over 2 pi times integration of that Im, let's take Im common, and integration of sine alpha would be minus cos alpha. So let me take the minus sign out. Cos alpha, this would be between the range 0 to pi. So this can be written as minus Im by 2 pi. Cos pi is minus 1. Minus of cos 0 is 1. Which means this entire value would be minus 2. Minus of minus cancel. We would get, and 2 cancel, we would get the value to be Im by pi. Which means in a half-wave rectifier's output current, the IDC value is given by Im over pi. This is one important quantity to remember. Now coming to the next quantity, which is the RMS value of the output current. This, we can represent this as IRMS. This is given by IRMS is equal to, as it indicates, RMS is root mean square. So the first thing is root, which is square root of, and we're going to take mean, which is over the time period, or the angle, which is 2 pi, integral 0 to 2 pi. So this is mean of square, the square of the current term that we have here. This is the RMS value of the current. So this can be written equal to, instead of taking the square root, it would be simple to write IRMS square, which would be simply equal to 1 over 2 pi integral 0 to 2 pi I square d alpha. So let us get this value found. That is 1 over 2 pi times, as we have the current 0 to pi a finite value and pi to 2 pi 0. So let's take that 0 to pi. We have Im square sine square alpha d alpha plus pi to 2 pi 0 d alpha. So obviously this term is going to be 0 and we don't have to care about this term. So IRMS square would be equal to 1 over 2 pi and integration of 0 to pi. So Im square can be taken out, and now integration of sine square alpha, which is sine square alpha is equal to 1 minus cos 2 alpha divided by 2 times d alpha, and the range is 0 to pi. This is equal to Im square over 4 pi. Now integration of 1 is alpha minus integration of cos 2 alpha is sine 2 alpha over 2, and over the limits this is 0 to pi. When we substitute this, we're going to get the IRMS square is equal to Im square over 4 pi, and alpha value, that is pi minus 0, minus the substitution of sine 2 pi would be 0 and sine 0 would be 0. Hence, this entire term of the second one would be 0. So we get pi here. So when we cancel the pi here, we would get Im square over 4, which means IRMS is equal to Im over 2. So this is another important quantity to remember. That is, for a half-wave rectifier's output current, the IRMS value is Im by 2. Now coming to the next component, which is form factor, which is simply a ratio of RMS quantity to that of the average quantity, which is the IDC. So this would be given by Im over 2, which we just found out, divided by Im over pi, which is pi by 2. Now if you look at the waveform that we had for the current, we had positive half and the second half was 0, the negative half, and positive half again present and negative half 0, and so on. If this value was Im and the DC component that we have seen is Im by pi, would be somewhere here, which would be less than 1 by third. This quantity, let me represent that, IDC, which is equal to Im by pi. And if we look at the RMS value would be Im by 2, which is in the middle. So this is IRMS, which is Im by 2. So we get an idea what is the DC component present in this waveform. That is this value. So what it means is, if you take the entire area in this graph in this region of 0 to 2 pi and distribute that uniformly, this is the height we would get, which is the IDC. Now the next parameter that we're going to look at is the RMS value of the AC output current. This is in fact the I dash RMS. We know that the output current is given by I, which is a periodic waveform. So if it is a periodic waveform, we can represent that in Fourier series. In Fourier series, we would have the DC component, which is represented by IDC, plus all the AC components together. Let's call that as I dash. So let's make it very clear here that the current, which is periodic, is represented with a DC component, and all the AC components together, we are saying this is AC component. Obviously for an AC component, as it says, the average value would be 0, right? So for this one, average quantity would be 0. So the only meaningful quantity we can take is RMS value of it, and we will see why we need this component. We'll see in the next video. But the RMS value of this AC component is what we're trying to find out here. First, we need to have what is I dash, which is given by I minus IDC. Now we need to find RMS value of I dash. That value, let's call I dash RMS, which would be, as it says, RMS for square root and mean of the I dash square d alpha. So before we proceed, the most comfortable thing to do would be, instead of RMS, let's find the square of it, which is 1 over 2 pi integral 0 to 2 pi I dash square, which is I dash is equal to I minus IDC whole square d alpha. Now we can write this equal to 1 over 2 pi integral 0 to 2 pi. We have I square minus 2 times IDC times I plus IDC square times d alpha. Now we can expand this, which is equal to 1 over 2 pi, the first one 0 to 2 pi I square d alpha, and the second one, which is 1 over 2 pi integral 0 to 2 pi. We have IDC, which is a DC component, which is a constant value. We can take this outside, which means I can represent that here, IDC, and I have this I times d alpha plus 1 over 2 pi times integral of IDC square. IDC is a constant value, so square is as well. So I can take this out of the integral, where integral of 0 to 2 pi is simply d alpha, which would be equal to 2 pi. So this quantity and 2 pi gets cancelled. So we are left with the first term. This is nothing but the IRMS square minus, we have IDC, and the rest of the component, this 1 over this, is nothing but IDC. So IDC square, in fact I'm missing a 2 here, so let me put that 2 here. So I have 2 times IDC square plus, from the third one we have IDC square, which means 1 IDC square can be taken out from here. This is equal to IRMS square minus IDC square. So what it means is, if you want to find the RMS value of the I dash, which is the RMS value of the AC component of the current, is equal to square root of IRMS square minus IDC square. So we're going to use this quantity in the next video for finding ripple factor, and we will see in detail what is ripple factor, and we'll go in detail and see other parameters as well. If you like the video, please press the thumbs up button, and if you haven't subscribed yet, please do subscribe, and thanks for watching.